So next, I'd like to introduce Brett Singer. He is a department head of Sustainable Energy and Environmental System at Lawrence Berkeley National Lab. A major focus of Brett's work has been on high-performance homes with the goal of accelerating new building standard and retrofits to improve energy performance, resilience, indoor environmental conditions. Today he's going to present on mitigation of fine PM associated with cooking. Brett?
Thank you, Renji. Can everybody hear me okay?
Yep.
Great, okay. Share screen. There we go. Great. So as Renji said, I'm going to speak today about the mitigation of fine PM from cooking. I want to just acknowledge that we wouldn't get to do any of this research without funding from some really great government agencies, the state of California, California Energy Commission, the Building America program of the U.S. Department of Energy, the U.S. EPA and their Environment Department sponsoring this workshop, and also Department of Housing and Urban Development. The basic outline, I'm going to talk a little bit today about performance metrics and standards for kitchen ventilation, measured effectiveness under controlled conditions, some issues with real world performance and practical challenges, and then some resources. As Dr. Vance pointed out the other day, I guess it was last week or 2 weeks ago, we have emissions of particles and other things, both from the cooking burners and from cooking itself. The burners, when everything's working fine, a gas burner is producing carbon dioxide and water vapor. The water vapor itself can be an issue, but a perfectly well-functioning burner is going to also produce significant amounts of nitrogen oxide, HONO, and even some formaldehyde, and then also ultrafine particles. Electric appliances don't produce the NOx, but do produce the ultrafine particles. And then the cooking itself produces both fine particulate matter and a lot of ultrafine particles, in addition to irritant gases. One of the common questions, induction burners are becoming more and more popular. I've seen very limited data, including a nice paper by Brennan Less, my colleague at LBL back in 2015. It does appear that induction burners produce many fewer ultrafine particles. This in part is because you lack the very hot surface of the electric resistance coil or the flame, and no NOx really. So I think there's a good work to be done to demonstrate some of the benefits of induction. So we're talking about mitigating cooking. Commonly, we call this under the heading of kitchen ventilation. The concept here really is to remove the particles from the kitchen or preferably even from the cooking area before they mix into the air around the house. So there's some different ways of doing this. You could have a device just above cooking. It could be a vented range hood or a vented over-the-range microwave. The word vented is really critically important. What that means is that the air that's being pulled into the device is then being pushed outside rather than recirculated back. You see on the microwave, for example, in that picture, all the microwaves will have a grill, and I'll talk more about this. They can either exhaust air to the outside or send air back into the kitchen. If you send the air back into the kitchen, you may get some small amounts of particle removal, but largely not so much. So it's really critical that it vents. You could also, in the bottom left, vent by pulling air down and then out and around and sending it outside that way. So we call that downdraft. Or you can have exhaust fans either in the ceiling or there's a picture. That's not the one from my childhood home, but actually in my childhood home, there was one of these fans in the side of the wall, or of course a window. We're going to focus today on the venting range hood as by far the most effective of these. So there are some standards and codes for kitchen ventilation. The most prominent is the ASHRAE 62 ventilation for acceptable indoor air quality. The California Building Code, just a couple of the state has statewide requirements for kitchen ventilation, and they use more or less the same requirements as the ASHRAE code. That requirement is that you either need a range hood, so something above the stove that moves more than 100 cubic feet per minute, or CFM, and has a sound level of less than or equal to 3 SON. So that's moderately annoying depending on your tolerance for sound. Those two requirements together were actually set a couple of decades ago based on what equipment was available at the time. They have not been updated, but the committee that manages that 622 standard is right now discussing whether those should be updated to make the requirements for sound, so quieter hoods, and that is an issue I'll talk about later. If you have a fan somewhere else, then you need to have higher airflow, because to get the same effectiveness, you need to move more air out of the kitchen if you're not moving it right from the place. Home Ventilating Institute offers some guidelines that roughly translate to about 100 CFM for a 30-inch range as a minimum, but they recommend about 250 CFM. It turns out those are pretty good numbers. Energy Star has requirements similar to ASHRAE 622. So that's one of the really nice things about buying an Energy Star home is you get this. And really this last point is very critical, the International Residential Code. So this is what we call a model code. So this is a code that's created to enable local jurisdictions. Most of the building codes happen at the local level. So it might be your city or your county. Sometimes there are statewide requirements, but this allows your county or your city to just adopt in large part a code that's been written by experts somewhere else. And that International Residential Code actually does not require kitchen exhaust ventilation. It sounds like it does, but there's a catch. It says when installed, you need either 100 CFM on demand, meaning you would turn it on, 25 CFM continuous, or you can use a recirculating hood if it's installed according to the manufacturer's directions. So it basically allows you to not have kitchen ventilation. And partly as a result of this, or largely as a result of this, there are homes being built around the country and have for decades been built without kitchen ventilation installed. So there's no ducting installed to even put range hood in, which makes it very expensive to add it later. And that's probably the single biggest problem here, because all the other problems I'm going to talk about with the quality of the range hood, users actually activating the range hood, none of that is possible unless you have the device installed in your house, and that's very expensive if you don't have ducting installed for it. So how do we discuss or talk about or conceive of the effectiveness of these devices? There's a term, capture efficiency. It was developed long before I got involved in this business. We're going to talk about it quite a lot here. It's basically just the fraction of whatever you produce in the cooking area that gets pulled up and removed from the house before it mixes into the air of the house. So this is obviously the ideal. The higher your capture efficiency is a source control. You're just essentially not emitting that into your house. I'm going to use the expression CE, or the short term CE, throughout the talk, because capture efficiency is a lot to say. So how do we measure capture efficiency? Well, there's some different ways to do it. We need some kind of a tracer. We need to be able to quantify how much gets emitted and then measure what gets removed. If we use carbon dioxide, helpfully, if we're using gas burners, they produce carbon dioxide, as we've discussed, and then we can quantify that and then measure the amount of carbon dioxide that's being removed in the ductwork above the range hood and being sent to outside. And you see here a couple of examples. So that the blue symbol is a capture efficiency of 90+%, and the red is a 7.5%. And one of the things you see is when you have poor capture efficiency, very often is because it's not continually pulling the air from the cooktop surface up into the range hood. So we've done a lot of work in the laboratory to quantify capture efficiency. This was a study we did back in 2012, and you see the capture efficiency from 0 to 100%. On the bottom is for front burners, on the top is for back burners, and then the x-axis is airflow. So as you increase the airflow, I think it's intuitive and not surprising that you would increase the capture efficiency. And it's much more effective in the back burners. If you're at that 100 CFM, you may be at 60% capture. And at 200 CFM, there's a range of maybe 70 to 95%. If you cook on the front burners, it's much more variable and much lower capture efficiency. And again, I think it's intuitive because most of the range hoods don't adequately cover the front burners. So you're farther from the flow up from the burner. One of the big questions is, do these microwaves that are put over ranges, are they as effective as a range hood? Two important things about the microwaves. First is that all of the microwaves I know of that act as range hoods can be configured to either vent to the outside or recirculate to the inside. And the recirculating is what you see in the schematic up top there. Very importantly, they're shipped, I may be wrong, but in the past, they've been shipped consistently as being in the recirculating mode. So if you want to make it into a venting range hood, you need to literally turn a fan, it's inside there, to get into that mode. So that's just an issue. The installers all know this. Hopefully it gets done right, but it's something that needs to be checked. And historically, these range hoods were not rated for the performance with the California code and the 622, but now there are many certified models that are. So we asked the question, do these over-the-range microwaves, OTRs, do the over-the-range microwaves have similar capture efficiencies as other range hoods? And there's a lot of data here, okay? But what you're looking at is you're looking at on the left side our front burner testing, on the right side is back burner testing, and then we either did it with 2 front burners or 1 or 2 front burners, and with different airflow. So we put together all the data we had from both microwaves and traditional range hoods that were all kind of in the same range of less than $100 to a few $100s. And these basically what you see is that, there's variability within each group, obviously, but largely they're similar. So the microwaves over the range are a fine solution. There's a lot of convenience that goes with them. And so we don't in any way discourage or have concerns. They're perfectly fine as long as they're venting and they're used. So we had another question, which was everything we had done initially was with gases. Obviously, the subject of this workshop is particulate matter. So we had the question of does the capture efficiency for cooking particles look the same as the capture efficiency for the gases? And focusing in this case on the combustion gases. So we did some experiments in a 121 meter cubed room. That's about 450 square feet for those less inclined to the metric. We cooked on the front burner where we did stir fry. That's the picture on the bottom there of green beans and a wok on high heat. On the back burner, we pan fried a burger on medium heat. And then we also did some stir fry on the back burner. We tested 4 of the 7 hoods that we had previously tested in the lab for capture efficiency. One of the really interesting points in this, again, Dr. Vance showed this in one of her slides where they repeated the same cooking activity several times. And no matter how careful you are, and we were extraordinarily careful to even prep the food with the same amount of time out of the freezer. You know, we use consistent food sources, so this is manufactured food. And even with that, the variability in the particles that got generated from test to test was about a factor of 2. So we had to do 5 or 6 tests each time. What you're seeing on the upper right is the results. This is the particle concentrations in the room resulting from these tests. On the top is with no hood, and then with a low speed and a high speed. So particle concentrations are lower when you run the fan on high speed. That's what we expect. That's the back burner. On the front burner, you see there's actually a lot more overlap. So this is what less capture efficiency looks like. It means that the particle concentrations in the room are much more similar. If you squint and look closely or just actually do the quantitative analysis, you will realize that the blue on average is lower than the red or the black, and the red is lower than the black. But there's a lot of variability from test to test. So when you see data with these things, I have not been able to get my cooking to be more consistent than this. Maybe others can do it better, but we try very hard. So you really do need replication. This plot is very complicated. Just talk you through quickly on what we're looking at is each column of data is a different way of looking at capture efficiency. On the left are 3 different ways of looking at the capture efficiency of the gases. And then the unshaded part is capture efficiency for different particle sizes. So the first, the greater than 6 nanometers, the total count of particles. And then in each of those bins, it's the number concentration of the particles in that bin from 0.3 to 0.5 microns, 0.5 to 0.7, et cetera. And for 4 different hoods. So there's a low cost hood on the bottom, a high performance hood on the top, and then this Energy Star and this mid-level hood in the middle. And what you see here is that when capture efficiency is high for the gases, it's also high for the particles. So that's really good. If you get good capture efficiency, it's going to work for the particles. Off on the right here, though, you see for the front burner, we know we get less well. We don't capture as well from the front burner. The wok is particularly difficult because it sends a lot of the gases and some of the particles kind of out from the stove. And you see that when you start getting to lower capture efficiency, especially below about 50% on the gases, then your particle capture efficiency can actually go down quite a lot and even significantly lower than 50%. There's some nice work done by Dong-Yoon Rim when he was at NIST with Andy Pursley and Lance Wallace. They looked at ultrafine particles in a manufactured house. So you see the layout of the house down below. They measured in the master bedroom, so they're looking at particles moving through the house. They were focusing on ultrafine particles, the nucleation of particles. So this was just the gas burner. And then what you see here is they looked at some different airflow rates, 2 different hoods, 4 different airflow rates. And you see much higher performance, better performance, higher removal with the high airflows than the low airflows. And they also saw a big difference between the front and back burners, as we had seen in our separate experiments. We've done some work in the field. We went into 9 houses to look at pollutant concentration. 6 of those had range hoods. So we set up equipment carts in the kitchen and then in a bedroom area, and we measured both gases and particles. Here are the 6 hoods, range hoods, pointing out the one on the left there has good coverage of the front burners. It's a big volume to capture the gases and particles, the plume as it comes up from the burner, and it has the best airflow. The one in the H5 in the middle there is directly adjacent to a wall. So there's kind of a barrier that helps limit the spread of the plume coming up. And then the 2 microwaves, H2 and H6. This is another complicated plot. We tested quite a lot of different variations of different cooking, cooktop, simulated oven, and also different speeds of the burner. And what you see very, very broadly is that first hood has very good performance across all the conditions. Some of the hoods, like 6 and 8, have very poor performance under some of the conditions for some of the pollutants. And then there's some stuff in the middle. And then 5 was the one that was against the wall. So you see that, creating that barrier actually helped. I'm not saying you should put your stove against the wall. It's just that the more open it is, the more chance there is for the pollutants to make it out into the air. So on this question of are they actually used? So having the hood, having it vented, excellent. We done large surveys where we asked people, okay, how often do you use your range hood? So this is a survey of more than 2,000 people who were living in homes built in Southern California between 2003 and 2010. We did the study in 2016. And quite a lot of people say that they use the range hood either always, very few say always, but a lot of, maybe a quarter of the people say most of the time, and half or more will say they use it sometimes or as needed. People who have range hoods that exhaust air to the outside actually say they use their hoods more than people that blow air back into the kitchen, which I thought was interesting. So they're somehow perceiving that the exhaust ventilation range hoods are actually working better and they're using them more. If you look at why they say they don't use them, the biggest difference or the biggest distinction, first of all, the biggest reason is that it's not needed. So people perceive that in a lot of cases it's not needed. And by the way, these were all homes that had gas cooking burners. This was SoCal Gas helped us reach homes that have gas cooking burners. So these are homes where it is most definitely needed for them to use their range hoods, but they perceive it's not. And the biggest difference between the two is that they say it doesn't work. And the ones who have the non-venting range hoods say that it doesn't work much higher. So that, again, I was impressed at how people could perceive these differences. So then the question is, do people actually use the range hoods as frequently as they claim? This was data from the study of 54 houses and 17 apartments in California, all had mechanical ventilation. We monitored the cooking burners with temperature sensors and the range hood, and they kept in activity logs. We were able to line this up when they cooked and when they used the range hood. The cooking in the houses actually was really predominantly for dinner, and then a little bit sort of focused around breakfast secondarily. In the apartments, it was more throughout the day, although still a big spike at dinner. And more cooktop. Blue is cooktop and orange is oven. So more cooktop used in oven. I think that's kind of what we all experience. What you see on the right is the black part. It's the amount that they used it, the range of when they cook. So it's the total number of cooking events in each house. Black is that they used the range hood entirely for the cooking event. Gray is that they used it for part of the cooking event. And the white is that they didn't use it at all. And you saw that most homes used the range hood for fewer than half of the events. And we did see, if this is looking at when they cooked more, did they use it more? And it's the houses down in the bottom and the apartments secondarily. And you see that when they cooked more, they did use the range hood more. So again, people are perceiving more of a need the more they cook, and they're using the range hoods more. So that's actually, I think, a positive. We have to get them to use it even more than this, but at least there is some rationality to it.
Hey, Brett, do we have maybe wrap it up in 2 minutes or so?
I can do, yes, absolutely. Okay. I'm on the slope. So the use did increase with PM emissions in the houses, but not the apartments. So in the houses, when we could measure quantifiable PM concentrations increasing, people were more likely to use the range hood. This is just a study from Canada, looking at 132 homes, more or less found the same things, except even less range hood use in these houses, some more window use in the summer. One of the big problems we have is that when we go into homes, the actual airflows in the range hoods are much less than the product certification tests. The reason we think for that is that it's just higher static pressure. There's basically more airflow resistance as installed in homes than in the test conditions. There's some guidance and resources here that will be available for people to see on the slides online. Simple range hood guidance is use low resistance ducting, make sure it's quiet at a reasonable airflow. You got to use it. Cook on the back burner. Back burners are much more effective. Use it more as needed. And then this is all the materials that were pulled out of the duct above my range hood when they replaced my roof. And there's a little damper. So this range hood would never have worked again if I hadn't pulled it off and fixed that. And then the summary, in the interest of time, I'm going to just stop there because these are the points that I've all brought up already. So.
All right, great, thank you.
Also just thank the colleagues who, including Dr. Chan there, who helped do all this work.
Well, thank you for an excellent presentation. I think we have one quick clarifying question. That was on slide 16. What's the purpose of the tin foil shown in your photo?
Oh, it was a method that we used to measure capture efficiency in the field. We would basically create, we'd use foil to line it so that we could create a condition of 100% capture, then making sure that everything that was produced as a stove came into the range hood. So we just use foil for to extend the hood down to the burner, and then we pull the foil up to test the range hood where the foil was out of the way, basically.
Great. All right. Thanks.